In this exercise, we will set up a triple integral for the volume of the solid, whose upper surface is formed by a portion of the ellipsoid 4x squared plus 9y squared plus z squared equals 4. This portion is then sewn onto a portion of the plane whose equation is 6x plus 2z equals 4. The two portions are sewn together to form one continuous upper boundary for the solid. The lower boundary of the solid is the plane z equals 0 or the xy plane, so that for the solid, the value of z is greater than or equal to 0. First, let us take a good look at the solid. Let us separately sketch the two surfaces that form the upper boundary of the solid. The graph of the plane 6x plus 2z equals 4 is simple enough to sketch. We take a look at the intersection between the plane and the xz plane. Well, x and z are the only variables in the equation, so we take a look at the xz plane. That's easy enough. The graph of the equation 6x plus 2z equals 4 on the xz plane is simply a straight line, with the x-intercept at x equals 2/3, and the z-intercept is at z equals 2. Then we generate the graph of the plane by translating this line on the xz plane in a direction parallel to the y-axis. And we have our plane. The ellipsoid is rather easy to visualize on account of the fact that it is centered at the origin and that we can use the intercepts. The x-intercepts are at x equals plus and minus 1. The y-intercepts are at y equals plus and minus 2/3. And the z-intercepts are at z equals plus and minus 2. Since the z values for the solid are supposed to be non-negative, we only need the upper half of the figure. Now the problem is to determine exactly which part of the figure corresponds to the solid. This front bulging part in the figure is actually not part of the solid we are after. While piece of the ellipsoid, the plane 6x plus 2z equals 4, and the xz plane do form the boundary for the solid. The plane 6x plus 2z equals 4 cuts under this front piece, so that the plane 6x plus 2z equals 4 is not part of the upper boundary as the problem specifies. So we take this piece out. The blue curve on the image is part of the intersection between the ellipsoid and the plane 6x plus 2z equals 4. We'll trim off the extra bit of the plane and we have our solid. We have another blue curve, this time on the xy plane. This second blue curve is the intersection between the ellipsoid and the xy plane. It is sometimes referred to as the trace of the ellipsoid on the xy plane. On the xy plane, z equals 0, and we get the equation of this trace by simply setting z equals 0 in the ellipsoid equation. And we get 4x squared plus 9y squared equals 4, which is the equation of an ellipse on the xy plane. There is a third blue curve, which is actually a straight segment, and is part of the line intersection between the plane 6x plus 2z equals 4 and the xy plane. To find an equation of the straight line segment, we set z equals 0 in 6x plus 2z equals 4, and we get x equals 2/3. For this exercise, we will attempt to write a triple integral or integrals for the volume with the volume element dv equals dz, dy, dx. That is, we integrate with respect to z first, then with respect to y, and then with respect to x. In order to set up the triple integral or integrals for the volume, we need to be able to set up inequalities for each of the different variables of integration, starting with the variable z. Since z is the first variable of integration, we must solve for z in terms of the other variables x and y, using the bounding surfaces of the solid. That is, we need z as a function or functions of x and y in the bounding surfaces for the solid. But we do not just use any bounding surfaces. The bounding surfaces that we use depend on the variable z. We need to follow the z direction or go vertically within the solid and determine on what bottom surface the solid starts and on what upper surface the solid ends. The bottom surface is easy to figure out. Well, the solid lies on the xy plane, so the solid starts on the xy plane, where z equals 0. Now for the fun part, the upper boundary. The upper boundary is more complicated. It is made up of two pieces. One piece comes out of the ellipsoid, another piece comes out of the plane 6x plus 2z equals 4. So one piece of the solid starts at z equals 0 and finishes at the ellipsoid. Another piece starts at z equals 0, then finishes on the plane. We turn our attention to the seam or intersection between the plane 6x plus 2z equals 4 and the ellipsoid. This yellow curve on the xy plane, which is the shadow of the seam intersection, is the projection of the seam intersection between the ellipsoid and the plane 6x plus 2z equals 4. So the flat face of the solid, the face on the plane 6x plus 2z equals 4, lies above the region on the xy plane enclosed by the line x equals 2/3 and the projection of the seam. At least for the portion of the solid that is bounded above by the plane 6x plus 2z equals 4, we can easily write the inequalities for z. The bottom part of this portion lies on the xy plane where z equals 0, and finishes on the flat plane 6x plus 2z equals 4. Solving for z on this plane, we have z equals 2 minus 3x. Hence, for this portion of the solid, 0 is less than or equal to z is less than or equal to 2 minus 3x. We then find the inequalities for y for this portion of the solid. Y is the next variable of integration. The variables of integration remaining for this portion of the solid are x and y. And of course, we turn our attention to the solid's projection on the xy plane. The projection on the xy plane is simply the region on the xy plane over which the portion of the solid sits. The portion below the plane, 6x plus 2z equals 4, or z equals 2 minus 3x, is this region enclosed by the two yellow curves on the xy plane. So let's focus on the xy plane. When we were setting up the inequalities for z, we had to look for bounding surfaces. Z, after all, is the first variable of integration. Y is the second variable of integration. So this time we are not looking for bounding surfaces like we did for z, but rather we are looking for bounding curves. And on those curves, we will have y in terms of x. Since y is the variable of integration, we follow the y direction in the projection under the plane z equals 2 minus 3x. Observe that within this projection, we start at this lower curve and continue uninterrupted to this upper curve. So we solve for y in terms of x in both the upper and lower curves. Recall that the upper and lower curves combined is the projection of the seam intersection between the ellipsoid 4x squared plus 9y squared plus z squared equals 4 and the plane 6x plus 2z equals 4. On the plane, we had solved for z and found that z equals 2 minus 3x. Because the upper and lower curves have their origins on the intersection between the ellipsoid and the plane, we get rid of z in either the ellipsoid equation or the plane equation. Well, what we are after anyway is an equation on the xy plane. We replace z by 2 minus 3x in the ellipsoid equation. Simplifying, we should get 13x squared plus 9y squared minus 12x equals 0. We leave the details to the viewer, but solving for y in this last equation, we get y equals plus or minus 1/3 times the square root of the quantity 12x minus 13x squared. The positive square root must be for the upper half, and the negative square root must be for the lower half. This makes writing the inequalities for y on the projection of the plane face of the solid straightforward. Negative 1/3 times the square root of 12x minus 13x squared is less than or equal to y, which in turn is less than or equal to 1/3 times the square root of 12x minus 13x squared. Finally, we're down to the variable x for the portion under the plane z equals 2 minus 3x. With only the variable x left, we'll look for the smallest and largest values of x within the projection region. One can check that the smallest value of x is at one of the x-intercepts for this yellow curve. So do you remember how we find the x-intercepts of a curve? Well, the x-intercepts are on the x-axis where y equals 0. And if y equals 0 for the x-intercept, it must be that 12x minus 13x squared equals 0. Or that x times the quantity 12 minus 13x equals 0. Which means then that x equals 0, or 12 over 13. Now for the region that we are looking at on the xy plane, recall that the right boundary, which is this vertical segment, has x equals 2/3. 12 over 13 is greater than 2/3. Hence, we strike out 12 over 13, and the smallest value of x in the region is 0. Also, the largest value of x is 2/3. And we have the inequalities for x. Now for the inequalities for the portion of the solid under the ellipsoid. We start over with the variable z again. The region on the xy plane and under the ellipsoid is shaded in orange. The ellipsoid portion starts on the xy plane where z equals 0 and finishes on the ellipsoid where 4x squared plus 9y squared plus z squared equals 4. Remember, since we are dealing with the first variable of integration, we are looking for bounding surfaces and in the z direction. We solve for z on the ellipsoid. We get plus or minus the square root of 4 minus 4x squared minus 9y squared. Since the solid is above the xy plane, where z is greater than or equal to 0, we use the positive square root for z on the ellipsoid. Hence, 0 is less than or equal to z, which in turn is less than or equal to the square root of 4 minus 4x squared minus 9y squared. Now for the variable y, the second variable of integration. We again turn to the projection on the xy plane. First, we label the bounding curves for the projection under the ellipsoid. We already are well acquainted with this curve. It's the projection of the seam intersection curve. The upper half is y equals 1/3 times the square root of 12x minus 13x squared, and the lower half is y equals minus 1/3 times the square root of 12x minus 13x squared. Well, what about this other curve? The curve is actually the trace of the ellipsoid on the xy plane where z equals 0. So the trace equation is 4x squared plus 9y squared equals 4. As an exercise for the viewer can verify we should get y equals plus or minus 2/3 times the square root of 1 minus x squared. Remember that we are now following the y direction to find the inequalities for y. Check that for the portion to the left of the y-axis, the arrows go uninterrupted from the negative square root curve to the positive square root curve. And we have the first set of y inequalities for the ellipsoid portion. Now, we must not forget two petites regions to the right of the y-axis. We must set up one separate y inequality for each of these little regions. This lower portion starts at the ellipsoid trace, where y equals minus 2/3 times the square root of 1 minus x squared, and finishes at the seam projection, where y equals minus 1/3 times the square root of 12x minus 13x squared. And so we have the second set of y inequalities for the ellipsoid portion. The upper piece is just a mirror image of the lower portion, so we should have similar inequalities, but with the positive square roots. We start on the curve y equals 1/3 times the square root of 12x minus 13x squared, and finish on the curve y equals 2/3 times the square root of 1 minus x squared. And so we have the final set of y inequalities. Now we just need to figure out the x inequalities for each of these pieces. Because x is the last variable of integration, determining the x inequalities entails finding the minimum and maximum values of x within each of the three regions. For the biggest of the three portions, the leftmost one, the minimum value of x occurs at this intercept of the ellipsoid trace. This means 1 minus x squared must be equal to 0. And so x equals plus or minus 1, and since the intercept we are after is to the left of the y-axis, x must be equal to minus 1 here. The maximum value for this region occurs on the y-axis, where x equals 0. And we have our first x inequality. Now the two little pieces to the right of the y-axis are mirror images of each other. They both start on the y-axis where x equals 0, and finish on the vertical line, x equals 2/3. And so we have the x inequalities for the two little pieces. With the complete set of inequalities for each of the four different portions of the solid, we can now write out the total volume of the solid as a sum of four triple integrals. For the first set of inequalities, the one for the portion bounded above by the plane face of the solid, working backwards and starting with the variable x, which is the last variable of integration, we have the integral from 0 to 2/3, then integration with respect to y, which goes from minus 1/3 times the square root of 12x minus 13x squared to 1/3 times the square root of 12x minus 13x squared. Integration with respect to z goes from 0 to 2 minus 3x. Inside the integral, we simply have the volume element dz, dy, dx. For the second integral, integration with respect to x goes from minus 1 to 0. Integration with respect to y goes from minus 2/3 times the square root of 1 minus x squared to 2/3 times the square root of 1 minus x squared. Integration with respect to z goes from 0 to the square root of 4 minus 4x squared minus 9y squared. For the third integral, that is integration on one of the little pieces, the one below the x-axis, integration with respect to x goes from 0 to 2/3. Integration with respect to y goes from minus 2/3 times the square root of 1 minus x squared to minus 1/3 times the square root of 12x minus 13x squared. And integration with respect to z goes from 0 to the square root of 4 minus 4x squared minus 9y squared. We make an almost virtual copy of this last triple integral for the fourth and final triple integral.